Hi, this is Crossdot and Nabla, and this is section 12.2 covering over graphs and level curves. And this is an extension of section 12.1, and where we're talking about graphing planes in 3D space. This is a more general application for this, right? And we're going to be looking at real valued functions of two variables. And what that means is just that you have two variables, x and y usually, and you input them into an equation, and that gets you one real output. And a way to like scale it back to 2 dimensions, for example, is saying that we have a real valued function of one variable, which would be something like y equals mx plus b. We have an input, or your IV, or your independent variable, and you have your output, or your dependent variable, which is because y is dependent on x, right? And in this case, we're just scaling it up into 3 dimensions. So right here, f of x, y, it's another way of saying z. G of x, y is also saying z as well. It's like the same thing as saying f of x, g of x, right? And we have the same ideas from here, just transferring it over. Independent variables for real value functions of 2 variables is x and y. So x and y. The dependent variables f of x of y. Your domain is your values of x and y. Values, and your range is values of x and y that work in the expression. So again, this is going to follow those rules of like discontinuity, holes, vertical jumps, etc. Like those rules are still going to apply. And actually in our next section 12.3, going over the limits of functions of several variables, we're going to be covering over the ways to solve those types of problems as well. Example 1, we have a multi-variable function, f of xy equals y over x plus x times y. If you want to pause the video, try this on your own. See what you notice about this graph, if there's any discontinuities anywhere. And yeah, let's jump right into it. So 1, 2, I see that we have the 2 on top, 1 on the bottom, plus 2 times 1. We're going to get 2 over 1 plus 2 times 1. That's going to be 4 for f of 1, 2. F of a, just plug in a everywhere. We see it. So we get 1 plus a squared. What's that? And then f of xy, and then we have f of 1 over x, x squared. So let's just do x squared over 1 over x plus x 1 over x times x squared. This becomes x cubed plus x. That's our final answer. And then part D is asking us what is the domain of f. So we can say for x, it's going to be all real numbers. Actually, no, sorry. For y, it's going to be all real numbers. Excuse me. For y, it's going to be all real numbers. X is going to be all real numbers. X cannot equal 0 because we have a discontinuity here. You can't divide by 0. For example, right? Like let's say that y was like any number, like right, like 1. Let's just say we're holding y constant. Let's just say y is equal to 1, right? So we have something like f of x comma 1 equals 1 over x plus x. This function cannot be defined at 0 because 1 over 0 is still undefined, right? If we were to graph this, it would probably look something like this, where you can't really get to here as a value, right? And that's part of like the problem with some of these graphs sometimes when you're like graphing them or trying to visualize them in your head, because like you're seeing 3D space in your head and you're imagining like how does this work? And what we can actually do is we have this thing called a level curve that helps us visualize shapes of curves more easily on like a 2D map, right? And again, going to some other rules as well, we have the vertical line test, right? If you remember from single variable math, like for example, this isn't a function because x has one input, but y has multiple outputs. Not possible. And like for example, an ellipsoid also doesn't match because it has two values for z, or two values of f of xy for a given x and y, right? Yeah. Example number 2 and 3, going back to like sketching and stuff. What we did from section 12.1, talking about cylinders, this is going to kind of be the same idea. So we'll just jump right into it. I'm going to always call this x, y, and z. Actually, I'll label these blue because it's easier for me to understand. And then I'm going to label the graphs in red. So this should be going like that. And then should be like that. And then lift it up. Lift it up. And you can shade it in. Like that. And that's how you would get the graph for this, right? Because, again, your y isn't going to vary. You can just scale it up like that. Oh, shoot. Cut. Ian, if you're watching this, cut this part. Cut. Okay. Shit. All right, the actual way to graph this is like this. It's gonna go off of the x-axis like this. And what it's gonna look like is 6 minus x squared equals z. We're gonna just call f of xy z. Is that it's gonna look like this. And it's just gonna create these cylinders pointing outward at right. And it's kind of a bad drawing, but you get the idea of what that would look like. It's just extending outward in the y direction. And then for this shape right here, this looks like it would be some sort of ellipsoid, but I'm not 100% sure, so let's just get right into it. Okay, let's just set one of our variables constant. Let's just set y to be constant for the sake of this real quick. So it's going to be 16, root 16 minus 4x squared equals z. And then it would be 1, 2, 1, 2. And then it would be going up like this and going down like this. 1, 2, 3, 4. 1, 2, 3, 4. And then we can connect it all together like this. And I'm basically just going off of these shapes given like this. If we just hold one of these to be constant, right, like this, then we can just visualize it like that. And then if z equals 0, if z equals 0, then we know that it has to be 4x squared equals, well, it has to be some combination of like 4x squared. Oh shoot, hold on. If we said that z equals z to be 0, we would have 4x squared plus y squared equals 16. Divide everything by 16. We get x squared over 4 plus y squared over 16 equals 1. And this is just a standard form of an ellipse for when it's 0, for when z equals 0. And essentially, you're also going to see that these ellipses are going to pop out throughout this. And you get closer and closer to the top. That's what the shape is going to appear to be, right? And that's part of that process, right? Last topic we're going to cover in this section is the idea of level curves. Essentially, it's what we were doing in this last part right here with all those ellipses, but we're going to show like the difference in like elevation or the difference in like distance from each position, right? So this is a contour map, which is the collection of level curves. And essentially the main takeaway for this is it's usually used to visualize 3D data in 2 variables. So like each line represents, in this case, each line represents some elevation, right? So right here, this would be 8,800 meters, right? And I think each jump would be 50 meters or so. Yeah. This would be 8850, 8900, 8950. And as you walk a little bit in the x direction, a little bit in the y direction, you go up 50 meters. You walk a little bit in the x direction, a little bit in the y direction, you get to 9,000, right? As you walk a little bit, you're gonna reach this. Over here, you have to walk a little bit farther to go up that same distance between those curves, right? You have to walk a little bit farther to go to the same distance. You have to walk all the way over here to reach the same change in your elevation as you would right here, right? These changes are important because it actually helps us understand what's the most steep and what are the steepest and most flat parts of an area, right? So like for example, this area right here is flat because there's no change in elevation within this interval at all. It's all the same elevation, right? Let's say it's like 8,000 something, right? If you're walking around, you're still at 8,000 meters, right, for your elevation. And for example, for sketching these level curves, it's going to take a little bit of practice, but it's not too terrible. We'll do the first example together, and then you can do example 5 on your own. So we have z equals -1, so just plug in our values for it, right? And as we know, ellipses can't have negative outputs. That wouldn't work. 0 equals 1 over 4x squared. This doesn't work either. I mean, it would just be a point. So if you want to graph that as a point, z equals 0. I guess that's good as well. 1 equals this. Kind of a bad drawing of the ellipse. Let me get a better sketch of that. That looks adequate for the purposes of this problem. And then let's see, equals 1. 4 equals 1 over 4x squared plus y squared, which is just also another way to say 1 equals 1 over 16x squared plus y squared over 4. And then we can get that stuff off also. this is going to be z equals 4. And then we have 9 equals 1 over 4x squared plus y squared. 1 equals 1 over 36x squared plus y squared over 9. And then this is our last level curve. It's kind of a bad drawing again, but ultimately you would get the idea of what this shape would look like for these level curves. So as you go out 2 in the x and then 1 in the y, you would be going up a level curve, right? But like but if you're walking the same distance and you're going up 1, then you're going up 4, then you're going up 9, you would think that this portion right here is steeper than this portion right here, right? Because for the same x and y you're traveling, you're going up way more on the z, right? So like, for example, if I had like 16, right, I would be going something like this, and this is going to be 16. This is kind of an exaggeration, but this is going to be z equals 16. If I go up 2 in the x and then 1 in the y, am I not going to be going a greater amount? Because you're going up 7 from here, you're only going up 5 here, right? So you would say that necessarily as you go up along this function, it's going to be steeper for values greater than values that are greater for z, right? So like, for example, z is greater than z16, it's going to be steeper than if z is 9, right? And then sketching the level curves for this hyperbola, feel free to pause the video and try this part on your own. And let's just get right into it. Already noticing a couple of things. Just jump into it. It's going to be -4 to me, x squared minus y squared equals 1. Like that, and then you would get that, and this is just going to be z equals -4, z equals -4. Same thing for -1. It's just going to flip the order of this. Then I'm going to use green instead to show the positive values. 0 just gives us a point at 0, 0, right? Actually, it would give us a transversal at like this. Let me use this in orange. It would give us like this straight line through everything, because it would be x squared minus y squared, x squared equals y squared, which means that for all values of x and y that are equal, the absolute value of them are equal, then you can plug that through. For 1, like this, but still ultimately reaching that same asymptote. For 1 right here, you're reaching that same asymptote. And then for 4, it would also be reaching that same type of asymptote. And even though these are kind of poor drawings, not y, it's supposed to be z equals 1, yeah, z equals 4, z equals 4, z equals 1, z equals 0, and so on and so forth. these are kind of poor drawings, but ultimately this is, I guess, like the way to understand these types of problems. Like you always just sketch them out, and then you can see like where it gets steeper and where it gets more narrow, right? And example 6 is our final problem. We have to find the domain for f of x, y, z of this function. So we see that we have a square root, right? I think the thing with the square root is that we need to know if it's positive. It has to be positive for a value to exist, right? So we know it has to be greater than 0. So not greater than or equal to 0, right? So we can just square everything and then get everything on one side. It's going to be x squared plus y squared minus z squared minus 9 equals 0. And then we get x squared minus x squared plus y squared equal minus 9 equals z squared. So given this, we can say that take the square root of this, we get square root of x squared plus y squared minus 9 equals equals z, but z has to be positive in this case, right? We can say that the domain for this has to be, so that x squared plus y squared minus 9 is going to, x squared minus y squared is greater than or equal to 9, right? So that means like it has to be outside of like this circle right here. Any values outside of that circle would work. And then we can go back to here and we can just look at the function in general. We can say that z squared plus 9 has to equal x squared plus y squared. And you can do like a whole bunch of like algebraic manipulation to like solve for this, but this is like the general thing you want to look for. That's like one part of it, and then the other part of it would be to solve for when it would be not defined, right? And you can also graph this too and see like 0, 1, 2 for f of x, y, z. See where that would be discontinuous. Yeah, that's pretty much it with this section. Thank you so much for watching. Hope you guys have a fantastic day.